Alrighty, we will get started. Thank you all for being here. I'm delighted to host today the AI Research Intensive, which is going to be covering a wide range of topics that are relevant to AI research. Our intensive has really two learning outcomes. The first of which is this is about creating an experience where you can pick up the practical skills required for applied deep learning work. We'll have hands-on live coding and live editing with method development, model training at scale, and deployment. And secondly, this course is designed over 2 days to teach you also technical writing skills that are required for applied AI research, including how to compose different elements of a full research paper. The speakers you'll be hearing from over the next 2 days are members and friends of the Harvard Medical AI Lab that will be using their real-world experience working on AI research to compose and present these ideas to you. I want to start by just introducing our schedule over the 2-day intensive. So today we will be covering a wide range of topics, including when you have two models, how do you compare them such that you can say one is better than the other? Later in the day, we have learning how to deploy your models. So here we'll be covering Docker, we'll be covering how to push your model onto Hugging Face. Later, Julie will be talking about software engineering fundamentals. Here you'll learn about best practices for coding, for using Git for software versioning, and using GitHub for collaboration. Then we'll go on to transformers theory, where we'll be covering some of the latest advances that transformers have had in the past year or two, and more importantly, how we can leverage them. Then at 1 o'clock, we'll have how one goes about the process of cleaning up code. This is especially useful when you have done some work and now you want to be able to have others reproduce the work, which is very key in all research projects. Then we'll have transformers practice, and here the focus will be on coding up different elements of a transformer and also being able to use them. Finally, one of the most practical libraries for deep learning has been PyTorch, and we will start with an overview of using PyTorch for an NLP application, and then go into one of the most common extensions of PyTorch, which is PyTorch Lightning, and here cover some computer vision. Finally, we will be closing today with talking about state of AI research. Tomorrow, we will also have some lectures related to both the coding and the writing components. And tomorrow we will cover things like how to critique a paper, different aspects of writing a paper, how to train a model, how to set up those pipelines, how to set up pipelines for evaluating your model. It should be an exciting 2 days. I want to thank my co-hosts for this, Elaine Liu and Xiaoli Yang, for helping put this all together. And I also want to thank the 19 speakers from the lab and friends that you will be hearing from today. So without further ado, in just about a minute, we'll get started with our very first talk by Xiaoli Yang, which is going to be on comparing two models. So without further ado, I'm going to invite Xiaoli to take the stage and prepare to share with you, and we'll get started exactly at 9 o'clock.
Thank you so much, Pranav. I'll just try to set up my slides first. Can everyone see this all right? Okay. Okay, it's 9 o'clock. Then here we go. Hello, everyone. Hello, everybody. Good morning. And this is Xiaoli Yang. And today I'm gonna talk about how we compare two models in machine learning experiments, and also in general, actually, when we do have several candidates to choose from, like how do we decide rigorously which one we would like to go with? So without further ado, let's go right into it. First of all, I would like to introduce some learning outcomes you will get from this lecture. First of all, I will introduce how you can choose appropriate test hypothesis for your problem, because to answer different test questions, it's important to give correct questions to answer. And there are several types of test hypotheses you can choose from, and it's important to understand them and understand the difference between them so that you can correctly answer your question with the appropriate test hypothesis. And second one, I'm going to introduce how to determine correlated data versus independent data. This is very important because with correlated data, you will need to use different set of statistical tests, because some statistical tests indeed require data to be independent from each other. So it's important to always verify what types of data you have. And thirdly, I'm going to introduce you to some assumptions underlying some common statistical tests we often use. Sometimes people will like overlook some important assumptions and use statistical tests freely on their data, but this will lead to invalid results, and we do not want that to happen on our publications. And finally, statistical tests sometimes are not really good at dealing with corner cases. For example, they are good at dealing with mean and average scores, but for some non-typical metrics, for example, AUC and ROC, how can we do that in that case? And then, so I will introduce you to bootstrapping techniques that will handle this kind of problem. So here are the learning outcomes, and we will start with our lecture with several motivating examples so that you have some concrete ideas of what kind of problem we're talking about in this lecture. So example one, suppose that you're choosing between two report generation models, and you want to compare the performances using blue scores. And you run both models on some examples. So here the question arises. Sometimes model 1 outperforms model 2, and sometimes model 2 outperforms model 1. Then how can you choose the better model in this case? And example 2, you may face that suppose you are working on developing a machine learning method that aims to assist pathologists in diagnosing lymphoma by looking at tissue images. And you really achieving some promising results using your model that is like 7% diagnostic accuracy, outperforming the pathologist's diagnostic performance of 68%. And you really want to make your improvement formal and put it in a publication. So you want to really check rigorously if your model outperforms the pathologist. How can you show that to editors, to journals? And example 3, suppose that you are choosing between two machine learning models on a data set, and you want to deploy the model. So one of the model achieves AUC of 0.96, while the other achieves 0.93. And the difference is really small, and you want to choose the better one to work with. How can you do that? So here are the 3 examples, sample examples we want to work with. And without further ado, I will straight jump into the choosing appropriate test hypothesis. And I will show this section by slightly modifying the 3 sample examples to show that how the test purposes of our examples can affect the result you get. So first, test for superiority. This kind of test is one-sided hypothesis test. And it aims to test whether one group is better than the other group by more than a stated margin. So there are 2 points I would like to make on this slide. First of all, a reminder on what is a one-sided hypothesis test. Recall that a two-sided hypothesis test is when we want to compare a variable of interest, for example, x, to a specific value, for example, 0. And we only care about whether or not they are equal. So we do not want it to be too small or too large. So we need to look at both sides of the possibilities. So this is called two-sided hypothesis test. But for one-sided hypothesis test is that when we only care about x being larger or x being smaller than a specific threshold. We only look at one side at a time. So this is called one-sided hypothesis test. And it's really easy to understand for superiority test because if we want to test for superiority, as the name suggests, we want to test whether one model is better than the other. So we are only look at the better side, that is one-sided. And some other comments on the stated margin is that the stated margin is determined by expert in the field. So why do we have that? Here is an example. For example, suppose you have a model that you want to compare with the pathologist's performance. And you say, okay, my model is performing 1% better than the pathologist. And you have proved it statistically that this 1% is significant. But one question that pathologists in real world might ask is that, how important do you think that 1% is? Like, how much difference in the real life will that 1% contribute in our hospital? So the reason why we have this stated margin is that we need to not only ensure our result have statistical significance, we also want it to have clinical significance. So we manually set a stated margin to say that, oh, we need our model to perform better than this much, so that we have a significant result in the real life. Sometimes this margin is 5%, and it's usual case, but it really depends on the situation, that what kind of problem you are dealing with. And this margin is usually determined by experts in your field. So if you are working on a medical AI problem, consult the medical experts in your group to determine this margin. Okay. So here is how I would modify the examples to make them test of superiority. For example, recall that we had in example 2, we are working on a machine learning method and comparing to a pathologist's performance. To ask a superiority question, you will ask, if your model performs better than pathologists by a margin of 5%, then by saying that better, we are implying we are testing superiority. And by defining 5%, we are giving a stated margin. And then you may ask, okay, I do not always see a margin specified. Sometimes I just say, oh, I just want to check if your model performs better than pathologists. Then where does the margin go in that case? So then in that case, we do not give a specific extra margin in that case. So that stated margin is 0% in that problem. Okay, next, test for non-inferiority. So test for inferiority is, again, a one-sided hypothesis test. And it aims to test whether one group is almost as good or as the other group by a stated margin. But as good, we mainly means is not much worse. And the much worse is defined by this stated margin. So how would I modify this example to make it non-inferiority test? Again, the machine learning methods compared to pathologists. So I would ask it in this way: how to check if your model is not worse than pathologists by a margin of 3%. This is very similar to superiority, but only changing better to not worse than. Finally, test for equivalence. This is mainly a combination of superiority test and non-inferiority test. This test aims to test whether one group is similar to another group by a stated margin. And by similar, we are meaning not too much worse and not too much better, just similar within a range. And as the name implies, when we are working on the same example, our question would become, how to check if your model is not inferior and not superior to pathologists by a stated margin. So you may still think, oh, these examples are still a bit hand-waving, so I will further make it concrete by giving null hypothesis for these three tests. So let's give some definitions first. Let X be the model 1 or baseline performance. So baseline we are referring to like pathologist performance, and Y be the model 2 performance we are comparing against. And we define the stated margin to be M. So this is usually the clinically insignificant amount, and beyond that, we consider it clinically significant. So for the superiority test, the null hypothesis is that we want Y to be bigger than X plus a possibly non-zero M. And for non-inferiority test, we want Y to be greater or equal to X minus possibly a non-zero M. By this, we are saying that, oh, we can tolerate some kind of inferiority, but not too much. And finally, the equivalence test, we are stating that we want the difference between Y and X to be constrained within an interval M. So in that, and also a note here is that although I use M on both sides, it's sometimes not necessary that we have to have equal length on both sides. For example, this can be M1, and this can be another number, for example, minus M2. They do not have to be symmetric. It really depends on the situation, depends on what number you choose. Makes sense. And finally, I would like to illustrate this point using one last diagram. So in this diagram, we again have the same definition of X, Y, and M. And let's first look at the axis. Say we have the value of X minus Y on the horizontal axis, and we put 0 in the middle, and 2 points on two sides, M and minus M, representing the margin in two directions. So it's easy to notice that in the area on the left here, X minus Y is smaller than minus M. So that means our model 2, represented by Y, it's clinically better than our model 1. So similarly on the right, X minus Y is larger than the positive M. So we say, okay, in this area, the baseline is better. Then the equivalent test is basically testing, given the confidence interval of value X minus Y, does it fall completely in the area in the middle? So if it falls between minus M and M, that means the difference between X and Y is constrained within this small region. If it is not, then they may not be similar enough. And similarly, the non-inferiority test is testing whether the value X minus Y falls in the area on the left of this positive M line. That means that we do not want the, so this 0 to M line represents the amount that baseline performs better than our model 2. So we do not want it to be too larger than M. So non-inferiority test is basically testing, okay, does the confidence interval falls completely to the left of baseline. And finally, for the superiority trial here, notice that if lands completely to the left of the 0 line, meaning that Y is significantly larger than X, but it is not larger enough to be clinically significant, as it doesn't line completely to the left of our stated margin line at minus M. So this is a statistically significant result, but not clinically significant result. Okay, just give me a second. So, okay, then we conclude our lecture on the test hypothesis section. Let's proceed into the short but nice section about correlated and independent data. So first of all, let's look at independent data. For independent data, we first require variables to be free from any interference from each other. So let me give you an example. Say we randomly sample 100 patients from a study, and then we record one scan, image scan from each of them to make a data set, then it's natural to think that, okay, each person is independent of another person, and we do have independent variables. And on the contrast, for data to be correlated, we require variables to be not free from any interference from each other. So an example corresponding to the last one is that, again, we randomly sample 100 patients and record their scans, but some patients are from the same family. But if the study really focuses on some genetic heritage, then this will be a problem, because patients from the same family, they share the same genetic heritage, and they may be put into groups like this. And within each group, they are correlated, but outside each group, they are not. And another more specific example is paired data. So that is testing two models on the same test set. So for each subject in the set, we are generating two metrics, one from each model. So that means metrics are correlated in pairs. So in this case, we also have correlated data. And next, we are, with the knowledge of correlated and independent data, we are going to introduce some assumptions underlying common statistical tests. Specifically, we are going to introduce paired t-test for paired observations. Okay, here we go. Before we introduce the dry definition or dry formula of paired t-test, let's first look at this modified example. Again, our old friend example one, but I added more details. So suppose you are choosing between two image captioning models and you want to compare the performances using average blue scores. You run two models on the same test set. So that means on the same test set means we have paired observations, right? And then you want to compare two models test for performance. So here is where the paired t-test come into play. And it does have some assumptions. So we want to check them one by one. First one, we require the dependent variables to be continuous. So dependent variables here are blue scores, and they are continuous, so check mark. And second, we require observations are independent of one another. This is a bit confusing. You may ask, okay, we have paired data. How can the observations to be independent from each other? But the answer is observations here are actually referring to differences between two models' performance, or you can interpret it like examples in the test sets are independent from each other. So the gist of a paired t-test is that we want to eliminate correlation between pairs and groups by putting them together, and so that there is no correlation between pairs and groups. The correlation is constrained within the pairs and groups. So all this second assumption means is that there's no correlation between the pairs. And last assumption is dependent variables should be approximately normally distributed. Actually, this is a little bit hard. I will put a question mark on this because, as we know, metric scores are rarely really normally distributed in real life. But there's a workaround for this assumption as we are dealing with average blue score. And this is called central limit theorem. So the theorem states, if you first have a population with constant mean and standard deviation, and two, you take sufficiently large random samples from the population with replacement, then the distribution of the sample means will be approximately normally distributed. So sample means here corresponds to our average scores. And according to the central limit theorem, we are safe to assume if we have large enough random samples, we can safely assume that our average blue scores are approximately normally distributed. And this may still sound a bit confusing. I will demonstrate how exactly we tackle this problem via a live coding section. Okay, just give me a second to set this up. Okay, here we go. Okay, here we go. Let me just quickly generate my sample data and load my data set. And here is my paired t-test example. Okay, so here is our problem revisited and with a little bit more detail. So we will look at two models' BLEU scores. And suppose that we denote the BLEU score from model 1 as X and BLEU scores from model 2 as Y. And suppose the test set has 500 examples. And then we compute their difference, D equals to X minus Y. So the first thing when we have the data is not actually perform the test, is to first inspect the data. So we would like to first read the data frame. Suppose we call it blues. Oh, typo. Blues. No, not the grammar. Wait. Okay, sorry about that. Blues, we want to read in the data set. I have generated one data set here is called BLEU scores. We'll read in that. Oh, wait, there's no PD. Here I imported it. Cool, solved. And then we print its header to see what it looks like. So basically here is model 1, model 2 with their BLEU scores listed below. And first, what we might be interested in. We might be interested in their means, right? Because we want to compare their average. Let's first have a general idea of what who has a larger mean. So let's say we want to look at its mean. Blues, sorry. So we say, oh, model 1 has a mean BLEU of 0.63 and model 2 have 0.44. So we would postulate that model 1 performs better than model 2. So we would, now we have our test hypothesis. And then we might be curious about, okay, are you normally distributed? We would plot its histogram and check distribution. Histogram, we will first look at model 1. Okay, not normally distributed, almost uniformly distributed, but we expected that. It's okay. Let's take a look at model 2. Again, perfectly not normally distributed, but that's fine. Okay, so now we face a problem. Our data is not normally distributed. How can we still use the paired t-test? So now let's look at the formula for paired t-test. This is the t-test statistic for this test. Basically, we want to take the average of the difference and normalize it according to its standard deviation over the square root of the sample size. And it is claimed that when the difference D is normally distributed, T follows a T distribution with degrees of freedom of n-1, n here equals to 500. So the gist of this one is that, okay, as long as we can make this T statistic eventually approximately follows the T distribution, then we're fine. Can we do that? Yes, we can. Actually, we do not need to assume that strictly that each D difference is normally distributed, because recall from the central limit theorem is that as we have large enough samples, the sample mean of D already by itself approximate the normal distribution. So this is like the average, the sample mean normalized by the its standard deviation and square root of n. So the T statistics still follows the normal distribution. So we do not have a problem with that. We can still use that by the blessing of central limit theorem. So with that problem solved, we can proceed to compute our statistic. In order to ease our computation, we can do some mathematics derivations to transform this T statistic into this formula. This is like completely mathematically equivalent. So, and then our question becomes, is D statistically larger than 0? recall that D equals to model 1 metric minus model 2 metric. So if D is statistically larger than 0, we can say that, model 1, the average blue score of model 1 is larger than blue score of model 2 statistically. And it is a test of superiority with one-sided test. So we will have null hypothesis of D greater than 0 and alternative hypothesis of D. Typo, sorry, smaller equals. Okay. Anyways, so let's compute the statistic. First, we want to compute we want to record some constants. N is equal to 500, and the difference is between these two models. And then the numerator, according to the formula, is the sum of D. And the denominator is a little bit complicated, it's a square root, but within it, we have the numerator is n times this squared minus the sum squared itself. And then we finally need to normalize it by n minus 1 as the denominator. And here is our statistic. Yeah, it should be correct. And we divide them together. And here is our test statistic. T statistic in the formula. And then we need to compare it to the critical value. Let's say we define an alpha value of 0.05 for the one-sided test. Significant level for one-sided test. And then we want to derive its critical value. Critical value, and we directly extract it from the stats package, 1 minus the alpha threshold, and its degrees of freedom is n minus 1. And then if T is greater than this critical value, then we print that model 1 is better. Otherwise, we fail to reject our null hypothesis, and we say fail to conclude superiority. So here is our code. Let's try to run it. Okay, so actually we have a result is model 1 is better. This is kind of expected because the mean between them, where is the mean? 0.63 and 0.44 is quite a large gap. So this is how we deal with non-normal data using paired t-test in this example. Okay, let's quickly go back to the slides. Okay, we are back. There's one extra comment I would like to make about the previous example. Is a bit caution. Notice that we used 100 observations for granted to say that, it's sufficiently large. Actually, this is the tricky part, is that you can never say definitely that a data set is large enough for you. It's usually like according to experience. And sometimes when your data is very skewed or has very heavy tail, it may take more time or more sample data for it to converge to a normal distribution. But for our data, it's like almost uniform. Is not a huge problem. It doesn't take. It's actually converged pretty fast. So, so the central limit theorem is not panacea. You can, when you have like above 25 samples. Usually statisticians say, oh, it's a rule of thumb to have more than 25 or 30 sample size to count as a large data set, but it really depends on the situation. If your data is really skewed or has a really heavy tail, then even 100 data is not enough. So make sure you do the sanity check every time you apply it, and make sure your result is valid. Okay. Here comes to our last learning outcome. Is just recall that just now we compared average BLEU scores. You may ask, okay, what happens if my score is not as easy as to compute as a average or mean? What should I do in that case? And what should I do if I do not know the distribution of my data? I cannot assume normality, even with central limit theorem. So here comes the technique of bootstrapping, and is used to treat this kind of problem. Let's go into it. So first, a bit of intuition for bootstrapping. Bootstrapping almost works magically, and the mathematics behind it might be a little bit too complicated. So here we will only do a really sketchy introduction of its ideology. So for bootstrapping, it works like, first, we assume that a sample is representative of a population. And then we keep resampling from the sample data set to produce representations of the true population. So we compute metric values from these representative samples of true populations in the hopes that it will their distribution will resemble the true metric distribution. So this sounds a little bit confusing. Let me show you with some graphs. So here, this graph mainly represents the whole process of bootstrapping. So let's take a look at the red bracket part first. Say the red bracket part represents the resampling process. Say we have a data set, and this is the first line represents the original observations, and the second line we say we resample first time. And bootstrapping mainly assumes that this resample represents is representative of the original observations. And since the original observations is representative of the true population, this resample is hopefully also representative of the true population. And similar for the resample number 2 and resample number 3. So we are hoping to use these resampled data sets to simulate or to mimic true resampling from the true population. And then we compute X, our metric, from these resampled data sets, and we put all of them together to form a distribution of X. And then we say, okay, I think this we believe this distribution resembles the true distribution of true metric X. So this is the main idea. And also recall that the reason why we want the distribution of a metric so badly is that once we know like its critical value or what probability of its value are at each of the intervals, it's easy for us to figure out confidence intervals, and also it's very easy for us to perform any test of superiority, non-inferiority, or equivalence. So the distribution is the key, and the key of bootstrapping is to simulate distribution. Okay, so now again, let's have an example. Example number 3. Suppose that you are choosing between 2 machine learning models on a checksum dataset, and you want to deploy it. One model achieves an AUC of 0.96, while the other achieves 0.93 on the same test set. So that means we have paired data. And how to decide if one model is better than the other? Oh, I think I skipped one slide. Okay, let's try to solve this problem using live coding. Check shifting screen again. Give me a second. Okay, we are back here again. So this time we are doing bootstrapping. And first of all, let me load my data set I created again. So recall that we were dealing with AUCs. So the data we use this time are the probabilities, the probabilities we have from models. Oh, I think I made a small typo here. It should be model 1 and model 2. It is not pathologist. This is a typo. I will fix it later from the dataset. So we are comparing model and model 1 and model 2. Let's use model and pathologist for this problem specifically, in case we get confused. So we are using probabilities, and here is how it looks like. We have labels, and we want to compare how each of them predicts true positive, true negative, like using the area under the ROC curve. So we want to write a bootstrapping function so that it can help us resample from our data set and compute our AUC metric. We have bootstrap. For this function, we want to input our data set so that we can resample from it, and n represents how many times we want to resample from our the original data set in order to create a population. Let's set it to default 1000. You can try 2000 or 3000 depending on your computation power. First, let's create a collector to collect the AUCs, and then we want to compute AUC for each sample n times, and here n equals to 1000. So we loop through this number of times, and for each sample, we need to first figure out how many sample we need to resample from the original data set. Usually this is equal to the size of our original data set. So it will be len of price. And then we create our bootstrap resample. We sample from it, and we say we want it to equals to the length, and we allow replacement, and then we fix a random state to make it reproducible. So this is sample with replacement. And then we want to use AUC function to compute it. Specifically, we are using scalar metric functions. We will first compute it for model. We will first figure out the ROC curve for it. First, we put in the true predictions, and we put in the probabilities model, and we need to set positive label. Let's say it's 1. Pos label, correct? Okay, correct. And then we do the same thing for the other model, the pathologist. Path, and path. We change this part. Path. Okay. Oh, this is typo. Okay. And then we figure out the AUC value. We simply use the default function model AUC metric AUC. We put in the output. And similar for the pathologist AUC, compute it again. And notice that we want, since our data is paired, we do want to compute the difference between them in pairs. We do not want to destroy this pairing relationship in order to eliminate correlation between them. So we want to record a difference in this AUC pair. and test whether the difference is huge enough to be larger or smaller than 0. So we would append it. Oh, probably it makes more sense to call it AUC's diff. Oh, I locked my screen. AUC diff. We'll append it to AUC's diff. We would subtract them. Okay. Then we want to return our collector. So for this function, we are basically doing, given a data set, return the distribution, the bootstrap distribution of AUC difference. This is what our function is doing. Okay. So as a final step, AUC is diff. We try to run our model. Put AUCs. Right. We want to sort it because we do want to rank them from the smallest to the largest so that we can extract the percentile. Plot and put AUCs. And we want to graph it to make it visualized. Let's see. It's not printing. Let's do it one by one. Oh, the indentation. Oh my God. Okay. Put AUC name error. Oh, typo. Sorry about that. It's computing thinking. Okay, here we go. So we can see that this is the cumulative distribution of our AUC's difference. And at the 25 percentile, we have negative 0.06. And at the 97.5 percentile, we have 0.03. So we do have 0 in the middle. So we cannot say that, okay, their difference is either larger or smaller statistically than 0. So we do not reach to a definitive, like rejective conclusion for this hypothesis test. We cannot conclude that model 1 is statistically better than the pathologist or model 2 in this example. Okay, so let's quickly go back and summarize. Final comment. So now we have studied statistical tests and bootstrapping, and it seems that bootstrapping seems always superior than statistical tests because it can deal with non-normality and it does not have to assume a distribution of the variables. So is it true that we always prefer bootstrapping? Actually, it is not actually. Because bootstrapping relies on the assumption that our sample is representative of the whole population. So it cannot avoid the problem of when the sample size is too small and it cannot generalize to the true population. It will be hard because say you have a really complicated distribution, but you only have 20 data points. How can you generate a really great bootstrapped distribution from that? It's hard, right? But if you do have variables that you know that follows a specific like normal distribution, you should always try to use this statistical test because you should take the distribution information for granted. It's provided to you, just use it, right? So bootstrapping is very flexible, but statistical test, when given enough information, is rigorous. So I think that's my final comments on this. We have achieved choosing appropriate test hypothesis, determining the data type, and we learned pair t-test, and a final flexible method about bootstrapping. So I hope you learned something from this lecture, and happy testing. Thank you so much.
Thanks so much, Xiaoli, for the wonderful kickoff right here. We are